In the last class, we looked at the Kachiyan-Minty problems and said that the Kachiyan-Minty problems would take 2 to the power n minus 1 iterations if there are n decision variables in the problem. We also saw that there could be indirect ways of overcoming this difficulty, particularly for the Kachiyan-Minty problems, and those ways of overcoming the difficulty could be to have a different starting solution, or it could be a different rule, entering variable rule could be different, or scaling the variables could also get us out of the Kachiyan-Minty difficulty. But we should keep in mind that the idea of the Kachiyan-Minty problem was not to solve the Kachiyan-Minty problem, but to expose the fact that Simplex algorithm, particularly when you use the maximum or the largest coefficient rule, the Cj minus Zj rule, can turn out to be exponential for certain types of problems. Now, the algorithm is called a polynomial algorithm if it takes the time taken to solve is a polynomial function of the problem parameters. It becomes non-polynomial, it becomes exponential when time taken can be shown to be an exponential function. At this point we are not going to go deeper into complexity, but we will, based on the Kachiyan-Minty example, understand that Simplex can take an exponential number of iterations, particularly when you are looking at Kachiyan-Minty. Kachiyan-Minty examples are very few examples that have been published. There could be many more which have not been published yet, but this was enough to show that Simplex is a worst case exponential algorithm and it is not a worst case polynomial algorithm. Now, the fact that it could be exponential was already evident by the algebraic method, which will take NCM iterations, or it evaluates all the NCM possible solutions. So, one could go back and perhaps argue that there are no Kachiyan-Minty examples for the largest product rule or the largest increase rule, but it would not be too difficult to create an equivalent Kachiyan-Minty example because they have been created for the largest coefficient rule. So, the main understanding is the fact that Simplex is an exponential algorithm when it comes to looking at it in terms of complexity. So, the next question that people started asking was, can we have polynomially bounded algorithms to solve linear programming problems? In this course we are not going to go very deep into the understanding of the polynomial algorithm. We will just give an outline or an overview of at least one of them, also try to explain some of the issues related to this. Now, when this question was raised, say after the Kachiyan-Minty examples were published, then people also started arguing that Simplex, however, was an excellent algorithm when it came to average case performance. It is only for the very small amount of Kachiyan-Minty and related problems it behaves in an exponential manner, whereas when you test it on normal problems that are taken from real life, problems that for which a linear programming solution is applicable, meaningful, practical, can be implemented and so on, in all those cases Simplex was only taking about 3m by 2 iterations on an average and very rarely going up to 3m. So, Simplex average case was a very good algorithm. However, average case performance of algorithms is meant for people who practice and worst case is meant for people who develop. So, theory still felt that Simplex is an exponential algorithm. Now, the question was, are there polynomial algorithms and how do we develop them? Now, when this thing was going on, there was also another issue that was being discussed, which is called solving inequalities. Remember that even though all the linear programming constraints are inequalities, there could be equations, but predominantly all of them are inequalities. We never tried solving them directly. We converted the inequalities to equations and then we solved them. That is because we know or we have learnt how to solve equations, whereas we have not learnt how to solve inequalities. Solving inequalities simply means, given a set of inequalities, can I find a solution? For example, if I give you say 4 or 5 inequalities of 2 variables, for example x1 plus x2 less than or equal to something, 3x1 plus 2x2 greater than or equal to something. So, you define a certain number of variables and certain number of inequalities. Now, solving these inequalities simply means finding an x1 x2 which satisfies all the inequalities, or if there are n variables, finding even one x1 x2 x3 xn which satisfies all the constraints is called solving inequalities. Now, when you represent the solving inequalities problem and solving equations problem, one may be tempted to think that solving inequalities is actually easier than solving equations. If you take a 2 by 2 set and plot the inequalities on the graph, and if you end up getting a feasible region, you can actually close your eyes and put your finger at any point in the region that will satisfy all the constraints. That is the solution to inequalities. Whereas you can't do that to equations. Most of the time there is only one point which satisfies all the equations. You could have other cases like no solution, infinite solution and so on. But in practice, actually speaking, solving inequalities is not easy. And people had not developed an algorithm that could solve inequalities, a polynomial algorithm that could solve inequalities till 1979 or so. Now, when this issue was being discussed, the ellipsoid algorithm was developed in 1979 to solve inequalities. It was a polynomially bounded algorithm to solve inequalities. We will not go into too much of detail on the ellipsoid algorithm, but I will give you some basics of the ellipsoid algorithm. Now, if you make an assumption that there exists a feasible region in certain number of dimensions, if you initially make an assumption that the given set of inequalities has a solution, which means there exists a feasible region for this. It is only a matter of finding a point which is inside that feasible region. So, the basic idea of the ellipsoid algorithm is to try and imagine a very large, the biggest possible ellipsoid of the same number of dimensions as the number of variables that you have. For example, if your inequalities has 10 variables irrespective of the number of constraints, you should imagine a very huge ellipsoid which is of 10 dimensions, and then create such an ellipsoid and locate its center. Now, when that center satisfies all these constraints that you have, then you have solved it. If you have not, then the underlying assumption is if the existing feasible region, if the center of the ellipsoid does not satisfy the existing feasible region, and if such a region exists, it is always possible to put that region in a smaller ellipsoid which is proportionately reduced in terms of volume. Okay. There are lots of governing equations and mappings and all that which we will not get into, but the underlying assumption is to just to put it on the blackboard. For example, if this is your region and if this is your huge ellipsoid, it need not be a circle, okay, if it is a huge ellipsoid and this is the center, right, if this is the center and it does not satisfy the feasible region, then you can always make an assumption that I can put something called a half ellipsoid which will be like this, whose center in this case satisfies, but if the feasible region is here, then the half ellipsoid center also will not satisfy. Now, how do you get this half ellipsoid from the bigger ellipsoid is a matter of a lot of rigor. I mean, so much of mapping, so much of equations. You cannot arbitrarily choose a half ellipsoid, it has to be proportionately reduced. All those is a lot of theory which we are not going to look at today, but we are only going to see the principle in which the algorithm was developed. So, you try to put it in a half ellipsoid and then try to take the center of the half ellipsoid, and if the center of the half ellipsoid again satisfies this, then you have solved it. If it does not, put another half ellipsoid from the given half ellipsoid and keep doing it. Keep doing it till it satisfies. This is the basic idea. There are a whole lot of issues associated with it. The most important thing being if there is a solution, then you have to prove that you will reach that point in polynomial number of steps, and that is the most important thing. And all those things were done, and we are not going to see how they were done, but all those things were done so that this algorithm was developed to solve inequalities. So this algorithm is called the Kachiyan's algorithm. It came in 1979, and Kachiyan proved that there is a polynomially bounded algorithm to solve inequalities. Now this was a major development, particularly when people were thinking about, can we develop a polynomial algorithm for simplex. Now the moment this is available, of course there are other issues, like for example, this is under the assumption that the given set of inequalities has a feasible region. So there are other issues like what if it does not have, what if it is not solvable. All those are in some sense a little more involved than even trying to understand the algorithm which will solve the case where a solution exists. So we will right now leave that, we will only take the learning from this part, that the principle is you start with the largest possible ellipsoid, get its center. Center does not satisfy, you assume that there are going to be two half ellipsoids and it will be in one of them, and then try to get that. It is not that you make 2 into 4, 4 into 8 and so on, it becomes exponential, but then you choose the one and go gradually reduce the volumes of the ellipsoids, identify the centers, and then keep proceeding till you are able to get it. Now when this algorithm was developed, then people said we can use this algorithm to solve linear programming problems. How do you do that? The linear programming problem is actually an objective function plus constraints. If I hide this, then this becomes solving inequalities, but linear programming is something more. Here this algorithm takes care of finding just one point among the many that may be available which satisfies this. But on the other hand, what you want is among the infinite or many available, you want the best. So you cannot directly apply this algorithm to this. So what people said is, let us do a small trick and get it. The trick goes like this. If I have a linear programming problem which is maximize Cx subject to Ax less than or equal to B, x greater than or equal to 0. Now its dual will be to minimize Yb subject to say Ay greater than or equal to C, y greater than or equal to 0. You can even, I mean you need not worry so much about the matrix notation, consistency of the matrices and so on. We will just take it crudely that this is how the dual will look like. Now what will happen is, your duality theorems have told you that if there is an optimum, at the optimum the Cx star should be equal to y star b, because the values of the objective function will be equal for both the primal and the dual at the optimum. So and your weak duality theorem also tells you that for every feasible solution to the primal and to the dual, this Yb is greater than Cx. So all you need to do is, you need to put Yb either equal to Cx or more importantly less than or equal to Cx. So the optimum to both, if you solve this set of inequalities, you have actually got the optimum to both the primal and the dual. To repeat again, from the weak duality theorem, Yb is greater than or equal to Cx, but at the optimum Yb is equal to Cx. So you change the constraint to Yb less than or equal to Cx. So the only point that will satisfy, the only xy that will satisfy this is the optimum, correct? And because you are dealing with inequalities, you do not want to put an equation there, because you may have to again convert the equation into two inequalities. So you just take it as the opposite. This is the opposite of the weak duality theorem result, but this is consistent with what we are trying to do. So add this one. So when you add this one, you get a set of inequalities. Your objective function does not come anymore. So you get a set of inequalities. So you are trying to solve a set of inequalities, apply this algorithm and try to solve it. So people said, if this can solve inequalities in polynomial time, now this can solve linear programming problems in polynomial time. But then there were other issues. The issue is very simple. Now, if this system has a solution, then there is no feasible region for this, there is only one point, there is no feasible region. So, this algorithm had to be modified to look at a situation when the set of inequalities has only one solution which is unique if it exists, whereas in the general case of trying to check whether the center satisfies the region, now it is more like defining the ellipsoids in such a way that ultimately the center will coincide with that unique point. So, that had to be looked at, and obviously this algorithm was modified, and then there were some perturbation schemes introduced. So, you try to put a small area around this point and perturb, and then check that you define a small feasible region around this optimum point, and then if it comes into that, yes, you say it is, you have to define the epsilons, and then you have to define the number of iterations in which it will converge into that, and all those things happened, and then people were kind of happy and convinced that the ellipsoid algorithm is capable of solving the linear programming problems in polynomial time. Now, when this was ascertained, and this the ellipsoid algorithm was the first algorithm in principle to be developed, not necessarily or not with the primary objective of solving LPs, but then it could be adapted to solving LPs in providing an algorithm that solves it in polynomial time. Then the next thing that people did is, let us try to solve some more problems in this. Now there is a theoretical proof that ellipsoid algorithm can solve it in polynomial time. Now let us try out some problems. If you go back and try out the ellipsoid algorithm for a simple problem like maximize 5x1 plus 6x2 subject to two sets of constraints and all that, ellipsoid algorithm will take at least about 1000 iterations for it to converge, whereas simplex will do it in 2 iterations. For example, if your optimum is x1 equal to 5, x2 equal to 4, say, what will happen is the ellipsoid will kind of alternate. It will start alternating between say 5.5 and 3.5 on one hand, and then 4.5 and 4.5 on the other, and it's like, you know, it will look at 5.5, 3.5 here, it will look at 4.5, 4.5, it will move a little bit closer, it will move a little bit closer, and then it will slowly try to converge towards this 5 and 4. So, what you have to do is you need to put an epsilon and say that the moment it comes within a certain range you terminate, but you do not know what that epsilon is. So, you run into those kind of difficulties, but what was evident from such a study, not by a single person but many people, was that this has a very poor average performance. In terms of average performance, simplex will just beat the ellipsoid algorithm hands down for the kind of problems that people were solving. People are not the researchers, people were everybody. I mean, in linear programming terminology, problems even with 500 constraints or 1000 constraints are considered to be small. It becomes large only when you are looking at a million constraints, a million variables and things like that. If you are looking at 50,000, 100,000, you are somewhere in the medium today. That is the kind of thing that's the kind of problem size that is associated with the definition of it being small, large, medium and so on. So, we are not looking at the 2x2s and the 3x3s that we are familiar with. If you want to look at a real life application that comes in say communication, or comes from scheduling in airline, or comes from forecasting demand in an airline industry or in an FMCG firm, or whatever be the example which can be modeled as linear programming related problem, then you are running into tens and thousands or maybe hundreds and thousands of variables. So, even when it comes to solving medium sized problems, the simplex was beating the ellipsoid algorithm, and ellipsoid algorithm had a kind of a poor average case performance, but it did have a very good worst case performance, which is polynomial. Now, when this was going on, then came a most important breakthrough, which is called the Karmarkar's algorithm. Which was also a kind of an interior point algorithm. So, if you go back to the simplex is not an interior point algorithm. Simplex is basically a corner point algorithm. It starts with one corner point and keeps moving along the corner points in a certain way, so that you reach the optimum, because you have a result that the optimum solution is always a corner point solution. For example, nothing, if this were a feasible region, in a 2 by 2 case, what Simplex would do is it would start here, it will either move here or here, and then check whichever is up. It keeps moving along the corner points. For example, nothing prevents you from starting with a point here, knowing fully well that it is not a corner point, provided you can move in the right direction from this. Not necessarily in one jump go to this corner point or this corner point and so on, but keep jumping in a certain way till you finally reach the corner point that is there. So this was the basic idea. Now such algorithms are called interior point algorithms. In a 2 by 2 you cannot actually appreciate the whole thing. If you can think of a 3-dimensional representation, then what you can do is you can be in an intermediate point, and then you try to move either in x or in y or in z up to a certain limit, and then keep moving that way. It is not that you just, it is not in one jump you can get here, you still have to move progressively. You have to make multiple jumps and then slowly move towards the corner point that is optimal. That was the basic idea of the Karmarkar's algorithm, wherein there are other mapped problems. You map all the x's into the y's and then find out, you try to put something into a huge a sphere of higher dimensions, which is something like your, it didn't use ellipse and ellipsoids, it instead used circles and spheres. So circles and spheres of higher dimensions, and then you solve a y problem and then get the optimum solution to the y in a certain way, and then map it back to x. So your x moves from a certain place from inside the feasible region to some other point inside the feasible region, and keep doing this back and forth till you reach the corner point. Now corner point, reaching the corner point is not exactly sitting on the corner point. It will be like you are within some 2 to the power minus n of the corner point, and then you will terminate. It is not that if the answer is 4 or 4 comma 5, it will beautifully sit at 4 comma 5 and tell you that this is the optimum, which Simplex would do. It would always converge at 3.998 and 5.001 if you are giving a 3-digit accuracy or whatever. If you want a 25-digit accuracy, then it will be some 2 to the power something error and so on. So that was the basic idea of the Karmarkar's algorithm. Now again there were lots of similarities and differences between the Ellipsoid algorithm and the Karmarkar's algorithm, and there are lots of research papers which talk about, maybe the basic idea is from the Ellipsoid, some people would say it is not, and there are other related issues about the origin. Both these algorithms came from scientists who worked in different countries which compete all the time. So there were issues of origin and so on, but that is beyond our discussion. Our discussion is only to look at algorithms that help solving linear programming problems. But then today it is accepted that Karmarkar's algorithm, which exclusively developed to solve linear programming problems, unlike the Ellipsoid algorithm, and perhaps a little faster. Both of them have a worst case polynomial nature of the algorithm and so on. Now the important thing is that the Karmarkar's algorithm should start with an interior point, which means the interior point implies that the point is inside the feasible region. So what Karmarkar's algorithm would do is, it will solve a particular problem. It will solve a particular linear programming problem for which the value of the objective function is 0 at the optimum. The point 1 by n, 1 by n, 1 by n, 1 by n is feasible, and so on. So there are certain conditions associated with the Karmarkar problem. The problem that he used as a base problem to develop the polynomial algorithm would satisfy certain things, at least some of which are the value of the objective function is 0 at the optimum, and the point 1 by n, 1 by n, 1 by n is feasible, and so on. But then he also devised a mechanism by which any problem that has an optimum can be converted into the Karmarkar form by suitably writing the dual, by suitably scaling some variables, and it is a slightly complicated way to convert a given problem into a Karmarkar problem. For example, if you take a simple 2 by 2 that you are very familiar with, if you convert it into the Karmarkar form, you will end up getting some 10 constraints and 10 variables and so on. it does not matter, it is still theoretically a polynomially bounded algorithm. Now once again you have to go back and look at, in terms of average case performance and complexity, Simplex was still better than Karmarkar's algorithm for small and medium sized linear programming problems. Only for very large problems which run into millions of constraints and tens of millions of variables and so on, the Karmarkar's algorithm could be faster than the Simplex. So this is where the theory is with respect to developing efficient algorithms for linear programming. But as far as this course is concerned, Simplex will be the algorithm that you will use to solve linear programming as well as integer and other kind of programming problems. But as people who learn operations research, one should be aware of the limitations of the Simplex algorithm and the availability of algorithms that are theoretically very superior, and depending on the size of the problem that is being solved, may be faster than the Simplex even for average case if the problem size is exceptionally large. For the kind of small and medium problems that people encounter in practice, Simplex is still the best when it comes to average case performance and general average running performance. So with this we will kind of wind up the discussion on how fast or how efficient the Simplex is. We have not looked at, for example, there are obviously results available if the given problem with 100,000 constraints is infeasible, or if the given problem with 100,000 constraints may be unbounded. One does not know, but then there are results available. Both the ellipsoid as well as the Karmarkar's algorithm, there are efficient versions. In fact, the moment the Karmarkar's algorithm came in 1984, nearly for 10 years there were papers which extended Karmarkar's algorithm to various situations, discussed implementation of the Karmarkar's algorithm, discussed their own experience in solving the large real life problems and so on. There is plenty of research available, and people should still be working in several places to develop polynomially bounded algorithms better than Karmarkar's in terms of performance. But then as far as we are concerned and this course is concerned, we would look at Simplex and keep Simplex as the algorithm to solve linear programming problems. So we will wind up the discussion on Klee-Minty problems as well as the goodness of the Simplex algorithm, and then we will move to the next topic today, which is called integer programming. Now we will start integer programming. We will also look at a few things here. We will give you an introduction to integer programming and explain why it is different from linear programming. We will also look at some formulations. We will also try to see that certain nice things can be modeled using IP, and then we will go to solving integer programming problems using, we will first look at the 0-1 case, and then we will look at the Gomori cutting plane algorithm, and then some all integer algorithms. That will be the topic of integer programming. Now what is an integer programming problem? It is a linear programming problem plus the condition that xj are integers. The moment you add an integer restriction, it becomes an integer programming problem. Now the question is, should the integer, then can I define integer programming problem as one which has a linear objective function, a set of linear constraints, non-negativity restriction plus an additional condition that variables are integers? The answer is no, it is actually beyond that. An integer programming problem can be a linear integer programming problem, it can be a non-linear integer programming problem, it can be both. So in terms of objective function, it can be linear integer, it can be non-linear integer. But common terminology would mean that if you say it is an integer programming problem, it means it is linear integer. Unless otherwise stated, integer programming means linear integer, but it could be non-linear integer. You could have non-linear objective functions. Now what do I mean by an integer variable? Integer variable, for example, if I have a feasible region to an LP like this, Now it simply means, like for example, if this is 0 0, say this is phi 0, this is 0, sorry, this is 5 by, this is 7 by 2, 7 by 2, and say this is 0 4, something like this, okay, something like this. Now what does integer mean? Integer would mean that, for example, a point here, say 2 comma 2, which is an integer point, is feasible, whereas a point, this point itself is not feasible to the integer programming problem, because it is not integer. So in terms of the integer restriction of the variable, there are two categories. One category is called an all integer problem, where all variables are forced to take integer values. You have 0 1 problems, where the variable can take either a 0 or a 1, it is binary, it cannot take a value 2 or 3 or whatever. The assignment problem that we have seen in the earlier course is a 0 1 problem. Xij is either 0 or 1, but then we solved it as a linear programming due to other reasons, but the problem as such is a 0 1 problem, where variables take either 0 or 1. And then you could have mixed integer programming problems. Normally when you say mixed integer, it means you have some variables that are greater than or equal to 0 and some variables that are integer. When you say a variable is integer, it means you are looking at this category. You have to explicitly say that it is a binary variable if it is a binary variable. When you say it is, the variable is integer, it does not include binary. So variables can be of three types: continuous, integer and binary. Continuous is greater than or equal to 0, which is in linear programming. Integer means it takes integer values 0, 1, 2, 3, 4, any integer, and 0, 1 means it takes either a 0 or a 1. Now when I say the problem is mixed, it could be any 2 out of the 3 or all 3. Once again, normally when you say mixed, it means it is continuous and integer. The 0, 1, unless otherwise stated, does not figure in a mixed problem, but in reality a problem may have all 3 types of variables. The 3 types are continuous, integer and binary, could be any 3. So typically you can have something like 6 or 7 different types of IPs. You can have a linear integer program, all integer linear objective function and all integer. You could have a linear and a mixed integer. You could have a linear and a 0 1. You could have a non-linear integer, non-linear 0 1, non-linear mixed, and so on. Moment you get into the non-linear segment, it becomes tougher, and within that if you get into mixed, it is much tougher. The only solvable thing in the non-linear is the non-linear binary. Non-linear binary is reasonably easy, because if the variable x is binary, any power of x is also binary, it is only 0 or 1, therefore it becomes simple. The only difficulty is when you have a product, you get into trouble there, but as long as you have an x that is binary, any x to the power n is also 0 or 1. So we will look at that as we proceed. So typically a linear programming problem has all these things. Let us look at the first one, the simplest one, with a linear and an all integer. So this would simply mean a linear programming problem with the additional restriction that variables are integers. So in a 2 by 2 case, you would go back and say this is my LP solution. Now I know that this point is not feasible because to the integer problem. All I want to do is to find out that integer point which has the best value of the objective function. Assume maximization. So I want to find that integer point which maximizes my objective function. Now what are the issues? Number 1, first and most important issue is, if this happens to be a corner point, if I leave the integer restriction, relax it into an LP and solve it, and if I say that this is the corner point solution, now the normal feeling that one would have is that the integer point that is closest to this corner point is likely to be optimal. A feasible integer point which is nearest to the corner point is likely to be the optimum is a very common assumption that we can make. That assumption need not be correct all the time. You can have a problem where this could be optimum. You can have an objective function where a point, a different corner point, a different integer corner point could be optimum. It is all a matter of how the constraints are defined and how the objective function is defined. It is not absolutely necessary that the feasible integer point closest to the corner point is optimum. That hypothesis need not be correct all the time. You could get a different integer corner point or a different integer point which is away from the existing LP. For example, this could be optimum. If this is 5.5 0, then 5 0 could be optimum, and so on. So that is number 1. Now, if we compromise and say that I am finding it difficult, I know that the nearest integer point to the infeasible corner point need not be optimum to the IP. However, let me try and find an approximation. After all, it cannot be a bad solution, because the LP optimum is here. I just put an integer restriction. It can't be a very bad solution, it can be a decent solution. So I want to compromise and I find out that point. Now I am compromising, I am not looking at the exact optimum, but I am compromising somewhere. We start doing that, then what we have to do is to round off this. So rounding off is most of the time seen as a very efficient strategy to solve IPs. So when you round it off, what will happen is, if you have n variables, then each variable is rounded off to its upper limit and the lower limit. So you can have 2 to the power n rounded solutions that are possible. Now 2 to the power n is not a polynomial number in n. As n increases, 2 to the power n is exponential. So yes, so 2 to the power n is exponential, and therefore rounding off is not a polynomial way of solving it, whereas you are always interested in algorithms that are polynomial, and you will not take an algorithm the moment it is established that it is exponential. And even if you do an exponential search and get these 2 to the power n and get the best, it is still not optimum, there is no guarantee. Therefore rounding off is not a very good strategy, even though it is followed by many people. You will also know that out of these 2 to the power n, there could be a very large number that would be infeasible, because when you start rounding them off on the higher side, for example, you will get points like this. This you will have 4 rounded points, and in this case it can turn out that 3 of them are infeasible and only 1 of them is feasible. You can also have a situation where none of the rounded points are feasible, but there is an optimum somewhere else. For example, you can create a feasible region like this. This is the LP corner point, and let us say these are the 4 rounded points, none of them will be feasible to the IP, right. You could have an integer point somewhere here which is optimum. So you can do that. I mean, these are all extreme examples, however they are relevant, because we are trying to understand the principles involved. So there are 3 aspects to it. 1, rounding is exponential and therefore difficult to do. 2, the best feasible solution among the rounded need not be optimum. And 3, you can encounter situations where all the rounded solutions are infeasible, but there is an optimum somewhere. Therefore one should not do this. One should try and formulate the problem separately and solve the problem separately. What are the other implications? Can I have an algorithm which will directly solve integer programming without using ideas from linear programming is another issue. If you look at it, this discussion was based on the fact that you relax the integer assumption, solve the resultant LP, and then try to get the integer optimum from the linear programming optimum. That was the hypothesis, or that was the assumption which led us to this discussion. Now, let us go back and see this. Let this be the feasible region. Now, what do we actually want to do? If I can identify all the integer points in this feasible region, and then I substitute all the integer points into the objective function, I can get the best, which is optimal. So, it is only a question of trying or to be able to find out all the integer points which are there. For example, your integer points are, the moment you start looking at it this way, these are your integer points and so on and so on. So, your feasible region for the IP is not continuous, it is a collection of discrete points. You see, this point is infeasible, this point is infeasible, whereas in linear programming your feasible region is convex, and the entire results of linear programming is built around the convexity property of your feasible region. So, you cannot directly apply results from linear programming and say I can do this, look at the corner point and so on. So, you need to still be within the linear programming territory and do things in such a way that the convexity is not lost, the convexity of the feasible region is not lost, and then somehow you try to get the integer corner point. Somehow you try to get a corner point to an LP which is integer. So, most integer programming algorithms are developed with that thing in mind. We will still be within the, we will always be solving LPs, because we do not want to lose the convexity property of the feasible region, and somehow do something such that the LP optimum becomes integer. Please remember that in all IPs, if you relax the integer assumption and solve it as an LP, and if the LP optimum happens to be integer valued, you have solved the IP, and that is the best thing that you can hope for whenever you are solving IPs. You solve it as an LP and you hope that the LP optimum is integer valued, so that straight away you solve the IP. If it is not, then you still do things which are under the purview of LP, keep solving LPs in successive iterations and somehow get the optimum LP to be integer valued, so that it is also optimum to the IP. Now, algorithms to solve integer programming problems are developed that way. Right. After this, let us go back and try to formulate some practical situations which are integer programming problems. Now, we start with one simple example which is called the grouping problem. Now, let us define the grouping problem and see whether we can complete the formulation. Now, let us assume that I have five points which are like this. Now, if you look at it normally, and if I ask any one of you to come up with two groups, you will quickly go back and say these two will form a group, these three will form a group. It is very obvious. This is under the assumption of minimizing the distance among the groups and so on. Now, how do we first formulate this problem and then try and solve them to get this? How can we formulate this? Now, one of the ways of formulating it is this. Even before we define the decision variables, let us look at this. If I know the number of groups and if I want to solve or identify the groups for a known number of groups, say 2 in this case, then what I can do is I arbitrarily define 2 points, 2 seed points called S1 and S2. Now, the moment I define 2 seed points S1 and S2, I will go back and try to find out the given points 1, 2, 3, 4, 5, I will try to assign them or cluster them around the seed points. That is a very simple thing to do. So, these two will go to this seed point, these two will go to this seed point. Now, what is the difficulty there? The difficulty is not in assigning or clustering around the seed point, but the difficulty is in creating the seed points. For example, if I had arbitrarily created my S1 to be here and my S2 to be somewhere here, then you will see that all the points will cluster around S1 and you will have a null cluster around S2. Now when I say that I want a group, in that case the first group will have all the 5 and the second will have 0, which means you have only one group. Now when I say that I want two groups, a group is characterized by the presence of at least one element. Therefore what I do is I try to not identify seed points that are different from the given points. I will simply go back and assume 2 out of the 5 given points as seed points, so that I know for sure that I won't get null groups. So I could assume this one to be S1 and this one to be S2. So I am guaranteed that this one will form a group, 5 will be in another group, and the rest of them will get mapped into different ones. Now if I am going to form my groups based on the distance criterion, then the moment I know these seed points, assume that I know these seed points, I can quickly do a distance criterion and form the groups. So what I want to do is a good way by which I pick 2 out of the 5, or in general if I want p groups, I fix p out of the n as seeds, and the moment I fix p out of n as seeds, because of my objective function which is to minimize distance, I will quickly cluster the rest of the points around the p seed points. Now these p seed points are called medians. Medians are nucleus points, nuclei and so on. We will call them medians. So the formulation will look like this. I have I points, I equal to 1 to n. I will first put this condition xjj equal to 1 if point j is a median, and xij equal to 1 if I goes to median j equal to 0 otherwise. And the formulation will look like this. This is under the assumption that I know that p, the number of groups that I want. So what I will do is my first constraint will be sigma xjj equal to p, right. So 2 out of the 5 will take 1 and the remaining 3 will take 0. Now whichever j is a median will take that xjj will be 1, if it is not a median then it will be 0. Now xij should be less than or equal to xjj, because if I am attaching, for example, if I am attached, if point 1 goes to median to point 2, then point 2 should be a median. If 2 is not a median, then 2 cannot build clusters around itself. You can build clusters only around the median. So xij less than or equal to xjj would imply that any point that is not a median can only be clustered around a median, and sigma xij equal to 1 implies that any I that is not a median can go to only one cluster, and then your xij is 0 or 1, and then you minimize double sigma dij xij, and your djj is 0. Distance between the point and itself is 0. So you assume that for the given 5 points you have a 5 by 5 distance matrix, okay, and if they are points here they will be symmetric, so you can define it that way. So you will get a formulation like this. So this is one example of how integer programming can be used to formulate a reasonably complex problem. You will know that the grouping problem is actually a very difficult problem to solve. This is called the p median problem or a k median problem, depending on whether you call this as p or k. It is called the p median or a k median, and this is the integer programming formulation of a grouping problem. This is an integer programming formulation of a grouping problem under known number of groups. You cannot solve this if the p is not known. The only thing you can do is you can solve for p equal to 2, 3, 4, 5 up to n minus 1 and then do something, but This is under the assumption that you know the number of groups that you want, and having given the number of groups, you want to get the best grouping that is possible out of this. So, we will look at other types of formulations in the subsequent lectures.